So let's recap. We have talked about QP, quadratic program. Then what about this? Now this is no longer QP. This can be any F. Now I assume this is convex. Okay, number one. Number two, I assume F is at least 2 times differentiable, so larger than 2. Okay, I write this. Then I can just do this. That means what? Why I talk about this? It's not just because this is easy. It's also because this thing exactly can be used to solve this thing. And this is the idea of successive quadratic program. Okay, don't spell a thing. What does that mean? Is the idea. I draw the picture, then you understand. So I have F convex, right? So probably something like that. Okay, then what? This is not quadratic because this is a polynomial. Let's say this polynomial is degree 5. Okay, what we do? Let's say this is x. This is our starting point x0. Okay, so my function value is here. Again, let me recap. The computer or us don't know the red curve. We only know the black dot. So at this point, we know where is it and the function value f. That means we know the x location. We also know the fx location. We don't know anything. So we compute gradient descent. And what's gradient descent? Gradient descent is we build a function that's quadratic and then we move to the bottom of this quadratic function. So what's the idea? Well, that means we are actually building something on top of the red thing. So the red thing and the green thing have to agree each other at this point. Okay, this drawing is bad, but you need to know the idea. So the idea is this thing QP, this is f. So the idea is how do you solve general f is to do gradient descent. But why it works? Because of this picture. Because the idea is now I want to mean f. So what I'm going to do, this is for loop k equal 1 to whatever. So what I'm going to do is 1 build a QP. What's this? This QP, this green thing. Okay, so I should use green color. So build a QP. What is this QP? So I have a f. This f is not the red f. This f is in green. So this f have a definition. It's on x subject to something. What thing? The current point xk. This is the variable. This is fixed. It's equal to what? This thing. What is this thing? The quadratic function that give you gradient descent. Therefore, this thing is f at xk plus the gradient at xk and then x minus xk and then what? We have the quadratic part. Usually we use a Hessian for the second order Taylor series, but now we don't know the Hessian. Let's say then I will have something alpha I here. This alpha is exactly the Lipschitz constant of the gradient. That means the largest eigenvalue of the Hessian. That means I do this, then this thing will be positive, more semi-definite than the Hessian of f. Okay. In other words, the picture is this thing is below, no, on top of the red thing. And then what is this thing? This thing is a quadratic function. So once I have this QP, what I'm going to do? Once I have a QP, then the second step is what? Arc mean this QP. Okay, this QP. So in other words, why we talk about QP? Why we talk about this? Because when you solve a general f, what you are doing is you have a point, you build a green curve. This is a quadratic program. You minimize this green curve. The process of minimize this green curve give you gradient descent, and then you move to here. And then now what? Now you are here. Go back to the point in the x. That means this is the now what? This is the second point. What is second point? This point is x1, and now you build another green curve again. Okay, this time the green curve looks like this. Then you move to here, and so on. So this whole thing actually is successive quadratic program. So therefore, understanding this give you how to solve this. And because arc mean of this give us what? Just give us gradient descent. So that's why how you solve a general problem is to run gradient descent. Okay, by alpha gradient f. Why you get this? You arc mean this thing on x, you get it. This has no constraint. So how do you arc mean this? Take gradient equals 0, give you a closed form solution. You get it. Got it, right? So this is the general idea. So that means what? If this is a special case, this is a general case, because this is more general, right? So all the property here should hold here. So what we have discussed yesterday, we have discussed we should put the step size alpha is 1 over L, where L is the Lipschitz constant of this guy. So if I have a general f, then I have the same thing, then I can do the same. So that means, so now I randomly make up some f. So for example, my f, okay, my fx now, let's say e ax minus b. Okay, I put the fitting in the power and let me make it this. Okay, let's say I make it this. Then this thing I can calculate the Lipschitz constant. Then how? Well, you know this is now what? This actually is e of gx, and you know what is gx? This is just composition of something. Then chain rule. So chain rule is this, right? Then this one, the Lipschitz constant is what? This one, the Lipschitz constant is a transpose a, right? What is this? Okay, you put it in, then you need to bound it by using the expression of e. So in the end, this thing, the Lipschitz constant somehow is the original Lipschitz constant either plus 1 or minus 1. I don't remember the detail, but it doesn't matter. So this is the idea. So that means what? For this kind of thing, you can do the same gradient descent. You just change the Lipschitz constant by some small change depending on this. Not necessarily this is e, right? You can say I put a log here, then you change. Okay, so this is how you do for any f. This is the idea. The condition is you need this to be true. You can differentiate 2 times and convex. So that means anything we talk about, go to here. So this is the first generalization. What the second generalization? The second generalization is this. This is the second generalization. We previously talked about this, right? Just larger than 0, right? What if I now have Sx larger than R? Okay, so matrix vector. This is my constraint. Then how? In the ultimate form, it will be this. That is fx mean this fx subject to any x inside a set C. C can be anything. Then this will be projected gradient descent. So now we are moving to a more general version of this kind of thing. So this is what we talk about today. And the first thing is let's talk about augmented function. So because we want to talk about constrained problem. So now I want to mean f. Okay, easy. But now what about this? We we have a C. The idea here is that all X are feasible. That means what? All X are legal. Here is that X outside the set C are illegal. There are multiple ways you can work on this. Now I give you a big picture. Here are the ideas. So now I have min F and then what? X in C. Here are the ideas. Number one. Okay, number one. I put this thing as an indicator function and I put it here. So what does it mean? This is indicator function. Is that indicator function of a point X is if X is in C, 0. If X is not in C, infinity, positive. And I want to min it. I don't allow this to happen. Because if I am at infinity, I cannot minimize it. This is the largest possible number, but I want small number. So this is an idea. Then this will have some real thing because you allow infinity. R infinity is not in real number. So then we have some funny thing. This is the first thing. Then it goes to what? Indicator function, extended real projection, blah 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 later. Second idea is we do something similar, but what? We don't go to infinity. We just say that we have a penalty function. What is this penalty function? This penalty function is a special case of this. Okay, actually I should say this is a special case of this. This is saying what? This thing gives small when X is in C, give big value if X is not in C. That's it. So this one is an extreme case of this. So this is a special case. I write this. Okay. So what is small? Small can be any number. What is big? Big can be any number. And depends on how you define what is small and big. So this is vague. An example can be this. What is the problem? X inside set C, right? Then what is this px? Px can be the distance between X and a set C. Then what is the distance between a point and a set? Then this is actually an optimization problem because you need to calculate the distance between a point and a set. So this will be what? The smallest y in C, that this is true, right? Then this is also an optimization problem. Now you see this is funny. You put this in, then this actually now have X and Y. So now your optimization problem have X and Y. And then you may say, why I put the half here? Why I can't put 100 here? Then this introduces the idea of penalty parameter. So in other words, actually you have a lambda here, which I put a lambda here. Then this is called penalty parameter. Penalty parameter means how important is this term compared to this term. If they are equally important, you say this is 1. If this is more important, then you put lambda very big. If this is not important at all, lambda is 0. If lambda is 0, that means you don't care. If lambda is very small, that means almost don't care. So this is called penalty parameter. And this exactly is the idea of regularization. So regularization is nothing new. It's just penalty optimization. Okay? And then just to let you know, for some very specific version of P, we call it log barrier. Then this go to some thing. For example, let's say X larger than 0. Okay? How do I make a P? So I can say this. So if I have this as my constraint set C, then what's my distance between X and C? By geometry, I have the C here. This is my point. The distance is this distance. If I have a point here, this is the distance. If I'm here, I don't care. So you can, for example, say the max of 0 and X, this is the point projected onto this region, right? This is a point. I subtract my point, take the distance. This is a distance, right? Then this can be my penalty function. Okay? Then I put this thing inside because this basically means I cannot escape from here. I want to be as close as possible. Because think about it. If X is feasible, X is positive, this is X. X minus X 0. If X is negative, this is 0. I want negative to be small. Closest thing for negative to be small as 0. Or here. Depends on which part. Okay? Then yeah, right? Because for the part that is positive, they cancel out. For the part that is negative, I want to encourage negative being small. So I go to 0. Right? This is one way. But then you can say, oh no, I don't like this. I put an L1 norm or other norm. Or for example, I put an E here. You can. Okay? Then this is one thing. Or you can say, okay, I know that log is this. So now I have log negative X, which is something like this. Okay? So what does it mean? It means I want it to be here. I don't want it to be here. So you can put a log here. So I put an E here. You can put a log here. It doesn't matter. Okay? So this is the idea. You put a penalty and you penalize X not here. So this is a penalty. The extreme case of a penalty is called indicator function. So indicator function is just extreme penalty. These are two things. So these are the general ideas. So basically the idea is you move this into the function. Then now what? If I do this and suppose my P is also differentiable, so I can do this, then what is this whole thing? I don't see this as a two thing. I see this as a new thing. So I just minimize this. Then everything I talked about previously works. I just need to know how to do this. Then it's done. Then there will be a problem. The problem will be how do you tune lambda? Yes, then this is a problem on its own. We don't talk about it now. So this is the idea. So this is the idea. So you have a constraint set C. Here's important. This line is giving you a special case. The special case is if you can write this down, then C looks like this. But there are some C you cannot write like this. Then you cannot write in this form. This form is the basic form for textbook for nonlinear program. Okay. For example, some C you cannot describe it by equation. You can describe it by a PDE. Then you have PDE constraint optimization. Then in this case you don't have this. Okay. So what's the method? I just told you penalty method. Okay. Or you can do modern approach which is called proximal. Basically is to do indicator function. That means you make things go to infinity. So this is modern. The classical is penalty. And for the interior point, there is something called log barrier. Or you use a dual method, duality, Lagrange. We will talk about all this except the penalty and barrier. Okay. So this is the idea. So suppose I want to have this, then what I do? I make it. So you remember I said this thing is what? This thing is X in C. I just now have an expression to represent what is X in C mean. X in C means Gx is 0. Then you remember what I said? If I have X in C, I don't need to write this. I remove this by saying this is now plus a P something. Okay. So here, what's a P something? This thing. I didn't write a P, I write a phi. write but the same idea. So I write p something. So this is the p something, and this thing is called a penalty function. So you penalize this is false. So if I want this to be 0, then what's the penalty? Done. So if this guy is 0, the norm is 0. If this guy is not 0, the norm tell you how much you violate being 0. Then easy. So for this special case, I can just take norm, or you can say I take anything that, for example, I can even put a square here. It's also okay, right? Then or I put absolute value here. It's also okay, right? So it depends on how you design. So this is the idea. So basically this is a penalty. And then these tags are basically telling you the trade-off, what does alpha mean, blah blah blah, not important. Okay. And then why we do reformulate? Because now the problem is easy. Previously we have this, now I have this, and if this thing is differentiable, I just see this thing as a big F, I just do gradient descent on this, then done. No need to worry about other things. So this is make the problem easier to do. What's the bad thing? The bad thing is, first, think about it. Your original problem is minimize this thing. What's the new problem? You have something new. Adding something new makes the problem a little bit harder. So in other words, this new problem is now at least as difficult as this thing. In many cases, adding this thing makes the whole optimization more difficult. So this is drawback. You're adding more on your problem. Of course, you're making it more complicated, harder. This is the first problem. The second problem, you often need to know what is this number. The problem is we don't know. Therefore, this is the drawback. Okay? There's a way to know this number, and the way is called Lagrangian multiply. But now, not yet. We are now in penalty method. So that's the idea. Make it easy to solve. What's the price you pay? You make the problem more complicated by having an alpha. You need to be chosen, which we don't know. You can't say this is 1. Why is 1? You have to explain why it is 1. Maybe 1 is bad. Who knows? Okay? And also, the problem is harder to solve. So this is an example. Okay? This is an easy one. For example, I want to minimize x subject to ax is equal to b. Okay? Then what? So what is this? Geometry time. So suppose this thing represents a polygon. So suppose this is ax equal to b. So all the thing on the line are solution. Okay? Let's say it's like this. What does it mean? It means minimize the norm of x squared. So this is the smallest norm is 0. So this is the surface. So in this case, where should be the solution? It should be here. This one have the smallest norm of x, and also on the feasible set. So this will be the solution. Let's say, okay, this is the geometry. But how do we solve it? Okay, this is what? This is x in C, right? Now we don't do this anymore. We say we add a px here. What's a px here? P is violating this. Violating this means this is non-zero. So I just do this. What's the problem here? We now need to know what is this number. We don't know. Doesn't matter for a moment. So we do this and think about it. If I solve this problem, and if this guy is 0, this is true, right? And then in this situation, if I can also minimize this, then I solve this problem. So that means there exists a funny alpha star such that when I minimize this problem, this is true. At the same time, this is minimum. That's the idea. Okay. This actually is a very old math. 40. Okay. And then what? Now here's another thing. Suppose I have this. Now this is a little bit complicated. This is non-differential. Okay. But what happens if I want to minimize this? This means what? This means my L1 norm smaller than epsilon. Because the direction of this thing is the same as the mean. I want this small and I also want this small. Then I can just add it here. This is good. But what happens if I want this to be large? If I want this to be large, I cannot just add it here. Because if I add it here, I'm saying I want this to be small and I want this to be small. Then it's possible this is become too small that this is not true. So when the direction do not agree, you need to be careful. Here the direction agree, so I can just add it here. Good. Because for example, if x is 0, let's say x is 0. Is this true? Yeah, then good. I don't care this part for a moment. If x is 0, this is true. Happy. Here, this part only means is this true? But let's say if I have this, what to do? Again, not focus today, but I just let you know there are many ways you can talk about it. First, suppose I have the different direction. You want this to be true, right? Then you minus. Who said you cannot minus? You can, right? That means what? If this is small, then this is small, but this is big. To force this is true. Then you can do this. So if I put a negative here, then this is convex minus convex. Then this is called DC program. Difference of convex. Then you need to do something else. But let's go back here. We are not yet go to too deep DC program. No. So let's go back here. So how do you solve this one? This is now convex. Differentiable, not differentiable. So you need something to solve it. We will go to proximal operator. Not today. This is the first way. What the second way? The second way is I see this as a C and I always do indicator function. Then I have this. What's indicator function? If this is false, infinity. If this is true, 0. It's a very crazy penalty function. Yeah, I can do that. Then this becomes something looks like projected gradient descent. So that is, I minimize this, I project to this. Then how do I solve it? It will be what? It will be gradient descent, right? X minus alpha gradient. And then what? I project it onto a set C. The set C is this thing. Then I just project it. Yeah, that's it. Then the question becomes, what is the projection onto L1 norm that is smaller than epsilon? Okay, then this is a next step. But the idea is the same. We know how to project onto alpha, just max. This guy is not simple. Okay, but later. Okay, so this is the idea. Or you can use some blah 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 blah. Okay, not now. Okay, this is now log area. This is a third way. So I want to minimize simple function ax plus bx plus c such that x is larger than 0. We know we just do project gradient descent. But what happened? I don't know how to do project gradient descent. I want to do as this. So what? I do this. So what it is? Minus log x. Why? Because this. So I minimize this. So the idea is I minimize this. Okay, this is my ax minus b. So this is x0. I want this to be true. So this is allowed. Here, not allowed. What is log x? Log x is something like this. What is the minus? So it's something like this. So you know this is infinity. So when x closer to this region, this thing goes up and it's saying you should not come here. You should go this way. So if I add this one with this one, okay, now it's very complicated. I don't know what does it look like, but imagine this thing plus this thing. okay, something like this, right? Okay, then yeah, let's say the alpha is some number, then you will what? Let's say the minimizer here, then you will stop here. Then this is not negative. Good, okay? This is the idea. Then how do you minimize this? X equal, then what? The gradient is 2ax plus b, what? Gradient, this thing, minus alpha, 1 over x. Yes, now your gradient is some funny thing. You have a log. Another thing, Lagrangian multiplier. So what is this? This one I'll talk about later. This one actually is called optimal condition. So suppose your C can be written in this form, then you just add everything in the objective function. So you can think of it as like what? This is actually a penalty function, right? This is the px, but I just put everything here. And also important, you need to see the direction I am agreeing each other. So h is smaller than 0. So I want this to be small, meaning if this is negative, I'm even more happy. If this is larger than 0, so then you either make the expression become negative, that means make it smaller than 0, or you do some other trick. Okay, so I do this. This is now what? This is my big F, new objective function. But this have a special name. We don't call it big F. We call it Lagrangian. So basically like this. This is a bunch of G. So I have a bunch of lambda. So this is inner product. This is a bunch of H. So I call it inner product nu and H. So lambda and nu are Lagrangian multiplier. Okay. And now I want to minimize this. For penalty method, this is the different. Penalty method means I don't care what's lambda and nu. I randomly choose some number. So lambda and nu are fixed. What's Lagrangian method? Lagrangian method is lambda and nu are also variable. So in other words, if I also think of this alpha is a variable, that means this is not argmin x. It's argmin x argmax alpha. Then this idea is not penalty method. It's Lagrangian multiplier. What's the idea? The idea is adding alpha will what? Will balance these two terms. I want to find the largest alpha such that they are balanced. Largest means what? Largest means this one I care, not ignore it. Because small, what does small mean? This is 0. That means I don't care. Largest means what? The largest is infinity. That means I only care about this thing. I don't care about this thing. Then there will be a best value of alpha. I find the largest alpha that somehow magically balance these two. Then this is Lagrangian multiplier. So therefore you argmax on the lambda and nu. Okay, so this is the Lagrangian multiplier. And now this problem is funny. This is not mean problem. This is a min max problem. This is a saddle point problem. So what is it? So in this direction, in red is down, but in this direction is up. So convex here, let's say this is on x, and concave here, let's say this is on lambda. And you are trying to reach this funny point. This is min max. How do you solve this? Okay, very easy. You have min on x, max on lambda, Lx lambda. Ignore the nu for a moment. First step, I don't see this. I don't see this. Just gradient descent. What's the second step? I don't see this. I don't see this. Gradient ascent or gradient descent by put a negative here. Yeah. Then this is how we solve it. Then this is the easiest approach. Okay. And then what next? This is Lagrangian multiplier. I add gh into the function, right? But what happened if so this is Lagrangian multiplier. Okay. This is Lagrangian multiplier. I add this thing here. But what if I add one more thing? I add another thing. So this is new. This is f linear term. F linear term. What is this? Quadratic term. So now this is new, right? So it's augmented. So what's the augmented? Augmented means I add a quadratic term. What is this? This exactly is the penalty thing I told you, right? If this is violated, that means this guy is non-zero vector. Non-zero vector, I just put a norm here to measure how much it violates. So you can think of Lagrangian is what? Lambda is also a variable. Penalty is what? I put a px here. What's augmented Lagrangian? I combine them. You will ask, why the heck do that? Because it improves the convexity on L. Why? This thing is what? Okay, recap. F is mu strongly convex if what? F minus this is convex. You remember strongly convex and convex? So if my F is mu strongly convex, means I subtract a quadratic term is convex. So what I'm doing here, this thing, look at it, is on x. This is on x, not lambda. Okay, this is linear term convex. This F, let's say is convex. So now I add, ignore this for a moment, I add quadratic thing. So this whole thing is now alpha strongly convex. Alpha strongly convex, that means only have one minima. Minima is unique. Then because now I have lambda and x, I have this kind of thing. When I solve for lambda, if I have multiple x, bad. So that's why I add this, I make on x unique. The solution is unique. So when I solve for lambda, happy. That's the idea. This is why you add a quadratic thing. And there's another reason later is on duality, but not yet. So you can think of this is make this whole thing on x from convex to strongly convex by alpha mark. Then this is what? This is a parameter. So I put alpha under subscript. So here's the idea. Variable, original variable, Lagrangian multiplier is called dual variable. This is a number you need to tune, and due to some magic reason, you usually select it between 0 and square root 2. I just put a 1 here. Okay, in this case you can put a 1 here. Okay, that means you make it one strongly convex. There is a lot of theory how to choose alpha. Not yet. Okay, when we talk about ADMM, then we talk about how to choose this lambda. And when we have this thing, then we will get ADMM. Not today. Okay, so let me try to recap. So we have the following. We talk about how to mean a QP. This generalizes to how to mean a F. This generalizes to how to mean a F x in C. This thing you have three ways. One is F plus penalty x. A special case of this is F plus indicator function, which you go to infinity. And this thing generalizes to F plus penalty x, but you have a lambda, and now x and lambda are variable. This is only on x. And this thing is called Lagrangian multiplier. Okay, it's called Lagrangian multiplier. And then what? And then this thing, if you add this, that means you put the thing to norm, and then now you put a tau here. Okay, then this is Lagrangian multiplier with augmentation. And actually, let me tell you, okay, this is Lagrangian, this is augmented Lagrangian. question, this will give you ADMM, okay, not today, okay, but this is the picture. So this is penalty, this is indicator, which will go to blocks, okay, this is QP, NEF, F with constraint, freeway, number 1, number 2, number 3, this is 1B, okay, this is the picture.